In this video, we'll continue talking about electronegativity. And so just to recap, electronegativity is the tendency of an atom to attract shared electrons. And so electrons that are being shared between two atoms in a bond can be skewed in one direction if one atom has a much stronger or much higher electronegativity than the other. And we have these kind of general guidelines which show you, well, if the difference in electronegativity is of a certain amount, how we kind of generally characterize the bonds. Now it's to remember that this isn't a cut and dry, oh, this is nonpolar covalent, this is covalent. These are kind of general guidelines. But just remember, as the change in electronegativity gets higher and higher, the bond becomes more and more ionic in character and less kind of nonpolar covalent, right? From very even sharing to very uneven sharing. And we see that as atomic size goes up, electronegativity goes down. As atomic number goes up, electronegativity goes up. That gives us this general trend in the periodic table. As electronegativity goes up as you go across a row, and down as you go down a column. And I have some values here we can use. And so the first example, we'll use CF4. And if you look at the electronegativity of carbon, 2.6, and the electronegativity of fluorine, right? So the change in electronegativity will then be fluorine's electronegativity, 4.0, minus that of carbon, 2.6, to give us a 1.4. And kind of by my eye, and kind of the table I've given you, we would call that polar covalent. So this kind of very uneven sharing of electrons. And we'll see what that kind of means. Well, what are the repercussions of that? Well, here's a little notation device. It's just an arrow, and the arrow points in the direction of the atom with the higher electronegativity, right? It points in the direction that the electrons are more likely to be. And on the tail, there's a little tick mark, which looks like a plus sign, because if the electrons are more likely to be around the fluorine, it would make the carbon a little extra positive because it has less kind of access to those electrons, you could say. And the other part of notation, right? So we can draw this arrow for each bond to show which way the electrons are skewed. We can also draw this little symbol here. That's a lowercase delta. Here's a bigger one if that makes you feel better. And we can write a delta negative around this fluorine to say it's slightly negative. And again, that's because the shared electrons, right, in this case, these two shared electrons in this bond, if they actually are more shifted to the fluorine, that fluorine will have a little more negative charge. So each of these fluorines will have a slightly negative charge. And then this carbon in the middle will have a slightly positive charge. So I can write that in right there. Kind of an exaggerated schematic. This is a bad drawing, I apologize. If I have the carbon in blue and kind of the probability distribution for its electrons, or where are its electrons most likely to be, and the same with fluorine in red, I've tried to show you in some kind of exaggerated and weird way that the electrons will spend more time, or will be more likely to be found around these fluorines, right? They're not kind of in the middle. They're not equal between the two, because fluorine has a stronger pull than carbon, because it's got a small size and higher number of protons. These electrons will shift towards the fluorine more. And you can also think about that's the direction that this arrow is pointing to. This arrow is pointing in the direction that the electrons will shift. And if just to compare that, because it's a bad picture, this is my picture of hydrogen gas H2, and we could say, what's the change in electronegativity here? I keep doing that. I really should stop doing that. Okay. The change in electronegativity here, well, it's going to be 2.2 for hydrogen minus 2.2. It's going to give us exactly 0. So these are shared completely evenly. And I've tried to show you, like, oh, look, they're like in the middle, right? So this would be a non-polar covalent bond, while these would be polar covalent. And there's kind of a spectrum in between, and if you're really radical, you could say that, well, the electron spends so little time near 1, we could consider it ionic.